Good day. Today we will be learning about the transmission of electricity. After today's lesson, we should be able to describe how electricity is transmitted, calculate the voltage drop on the power loss in electricity transmissions, state the advantages of using alternating current over direct current for transferring electrical energy, and state why electricity is transmitted at high voltages. So, how is electricity transmitted? Well, it first starts at the power station. This may be nuclear, hydro, or the regular old fossil fuel type of power station. After the electricity is generated there, it is then passed through a step-up transformer, which will take it from a mid-level voltage up to a very high voltage. This varies from country to country. Some countries is 100,000 volts, 200,000 volts, 300,000 volts. It all depends on the country and how far they have to distribute the power. After it is distributed, then it will meet a step-down transformer, which will bring down the voltage from hundreds of thousands of volts to the required amount. So if it reaches a factory, they may need around 26,000 volts or 70,000 volts. It all depends. And your secondary customers, your basic buildings and homes, those need around maybe 120 volts, 100 and 240 volts. So when transmitting electrical power, the voltage gets degraded. This is what is known as the voltage drop. Every couple hundred miles or so, the voltage needs to be stepped up again. So the voltage drop is calculated using the formula V equal IR. As well, when the electrical power is being transmitted along great distances, some of the power is lost in the form of heat because of the current in the wires. This loss in power is calculated using the formula P equal I squared R. So let's do an example. Consider transmitting a block of power of 10,000 watts through cables that have a resistance of 16 ohms using a voltage of 500 volts. Also, consider transmitting the same block of power through the same cables but using a different voltage, this time a much higher voltage of 10,000 volts. For both cases, calculate 1. The maximum current in the cable, 2. The voltage drop along the cable, 3. The power loss in the cables, and 4. The percentage of the power that is lost. Hence, state which voltage is better for transmitting the 10,000 watt block of power. So, for both cases, let's see. The current will be calculated using power divided by voltage. So, for the low amount of voltage, the current will be 10,000 watts divided by 500 volts, which will give you 20 amperes. And for the 10,000 volts, the high voltage, it only works out to 1 ampere. The voltage drop is calculated using V equal IR. So when it is the low volts, which produces 20 amperes, then there is a voltage drop of 320 volts. But for the high voltage, which only produces 1 ampere of current, the voltage drop is 16 volts. So in other words, if you use the low voltage of 500 volts, 320 of those volts will be lost along the transmission line by the time it reaches to the customer. That is more than 50% of the voltage. And then if you use the high voltage, only 16 volts will be lost. 16 volts compared to 10,000 volts, that's a drop in the bucket. How much power is lost? That is calculated using the formula P equal I squared R. So for the low voltage of 500 volts, the power that is lost is calculated using 20 ampere squared times 16 ohms, and that gives you 6,400 watts. For the high voltage, it only works out to 16 watts. Comparing those, that is a very high amount of the power that is lost, 6,400 watts compared to 10,000 watts, and only 16 watts compared to 10,000 watts. So what percentage is lost? 64% of the power is lost if you transmit at a low voltage of 500 volts. That's almost 2/3 of the power. Compared to transmitting at a high voltage, only 0.16% is lost, a fraction of a percent. So in other words, it's almost 100% efficient. Not quite, but almost there. So, to wrap up, electrical power is distributed using alternating current at high voltages. Why alternating current? Because the voltage needs to be stepped up or stepped down, and transformers can only operate on alternating current. A transformer cannot operate on direct current because electromagnetic induction requires a changing magnetic field. Remember, that is Faraday's law. Direct current is steady and thereby produces an unchanging magnetic field. It is important to note that in theory, the only way a transformer could use direct current is if the DC was switched on and off very rapidly. Alternating current is normally produced at around 50 or 60 hertz. That's a frequency of changing direction 50 or 60 times every second. So in theory, if you could turn on and off direct current at 50 or 60 times a second, then you could transmit using direct current. But it's very impractical, highly impractical. Who can turn on and off a switch at 60 times a second? If you were able to do so, the switch would break off very quickly, right? And why is electricity transmitted at very high voltages, normally around 100,000 volts? Why? As we previously seen in the example, it's because power is lost. Very little power is lost at high voltages. So thank you. That is our class for today.